All right. Welcome everyone to today's program on forensic toxicology, methods used, and common errors. Yesterday, we had a great introduction to the topic from Dr. Andy Evans. You learned a lot about chemistry and how drugs enter the body, how they behave in the body, and about several types of drug screening tests. Today, we have with us Dr. Kieran DeCall, who is going to be presenting on toxicology tests that can be performed in a laboratory. And after hearing from Dr. DeCall, we'll have Dr. Evans back to talk about reading lab reports and go over some case examples. So most of you, I think, were here yesterday and got to meet Dr. Evans. Dr. Evans has a PhD in pharmacology and is board certified in toxicology. He has extensive experience working in research and serving as an expert witness in cases involving pharmacology and toxicology. And then also today with us, our first presenter will be Dr. Kieran DeCall. He has a PhD in human toxicology. His postdoctoral training was in the neurotoxicity of organophosphate warfare agents. He's board certified in toxicological chemistry and is a diplomate in the American Board of Toxicology. He has clinical and forensic toxicology research experience using the, mass spectrometry. He's based in Apex, and he works as a part-time lab director and also as a consultant for clinical and forensic toxicology labs. And he is experienced in the interpretation of forensic toxicology lab reports. So I welcome Dr. DeCall to the program, and I will now turn the floor over to you. Thank you so much, everybody, for being here. And I have you muted, Dr. DeCall. Let me get you unmuted.
All right.
Okay.
Thank you, Sarah, for nice introduction, and welcome everyone to my presentation.
All right, we're seeing your slides now. Looks good.
Okay, good. So today I'm going to present about laboratory drug testing, more in the techniques and principle behind the test. This is the outline of my presentation. I'll cover 4 sections in this presentation. Sample validity test, basically the validity of the urine specimen, immunassay drug screening methods, confirmation of drug testing by mass spectrometry, and laboratory quality assurance of testing result. The first part is specimen validity testing for urine specimen, because urine specimen is unobserved collection. The donor collects the urine himself and presents it to the lab personnel. So we need to determine the validity of such specimen. The first test for sample validity is a creatinine test. Creatinine is a small metabolite present in our body and in our blood that gets into the urine. It is formed in our muscle from everyday wear and tear, and is presented in the urine at a very high concentration, around 80 to 200 milligram per deciliter. How do we test creatinine? We add a reagent called picric acid to the urine specimen, and creatinine reacts with that picric acid and forms a colored complex. When we pass a light through that solution, that urine sample, then it will absorb a light of certain wavelength, and it gives a absorption signal in our computer, and we collect the data. So higher the creatinine, more absorption; less creatinine, less absorption. This way we determine the concentration of creatinine. Another test for urine validity is a specific gravity. The specific gravity, in simple word, is density of a liquid. when we the density term refers to the solid object, but when we describe the density of liquid, we compare with water and then define it as specific gravity. So what is specific gravity? So that is density. So when you have a few dissolved chemicals in a liquid or urine, then you have a low specific gravity. When there are a lot of dissolved chemicals in urine, it will give a high specific gravity, higher density. So there are a lot of dissolved small chemicals, small molecules in urine specimen. It is distinct from water. First thing, it has a distinct yellow color. And the specific gravity is based on one specific type of chemical or chloride ions. So chloride ions are present in our body. Chloride ions comes from our salt intake as well. When we have a few chloride ion, it will give a low specific gravity. When we have a lot of chloride ion, it will give a high specific gravity. In other words, chloride ion concentration is a proxy for specific gravity. How do we test a specific gravity? We use a reagent called iron perchlorate. We add this reagent in the urine specimen, and then it forms a chemical complex called ferric chloride. And when we pass a light, a purple light through it, it absorbs that light at wavelength 340 nanometer. And we get a nice absorption spectrum. And based on that, we determine the concentration of chloride present in the urine specimen, and that tells us the specific gravity of the sample. Another important characteristic of urine is urine pH. pH is the measurement of hydrogen ion concentration. Hydrogen ion comes from acid. So when you have a lot of hydrogen ion, it will be acidic. It will have a less pH, pH in the range of 1, 2, 3, 4, 5. When there are less hydrogen ion, the pH is high. It is in the range of 11, 12, 13, 14. So around 7 is a neutral pH, neither acid nor basic. So how do we measure? So this gives a clear picture of characteristics of a good urine. So what we are looking at urine validity, if you look at the front small circle, the specific gravity, given that the water has the specific gravity of 1, the ideal urine, the normal urine should have the specific gravity in the range of 1.003 to 1.0035. And the normal creatinine concentration should be 80 to 200 milligram per deciliter. And normal urine, human urine, has pH of 4.6 to 9.0. So any deviations from these parameters is considered diluted urine, substituted urine, adulterated urine will come into the specific definition of each type later on the presentation. So what is diluted urine? If the creatinine concentration is 20 or below and the specific gravity in the range of 1.003 is a diluted urine. What is substituted urine? When creatinine concentration is less than 2 and the specific gravity close to water is substituted urine. And the outer circle shows the water, which has the creatinine 0, no creatinine, and a specific gravity of 1 as compared to water, urine. Another validity test is whether the urine is adulterated or not. The most common adulterating agent are oxidizing chemical such as nitrite, chromate, bleach, iodine. And people use these very reactive chemical to tamper their drug testing. So simply when they collect the sample, they mix one of these chemicals into the urine and then send it to the laboratory. How does this oxidizing agent tamper with the drug testing? So, it interferes with the immunassay drug testing, and we'll later know in the presentation how the immunassay work. But in general, immunassay consists of an antibody as a reagent, which captures the drug of interest. So these oxidizing agents chemically interfere with drug antibody interaction, or they may attack the antibody itself, and they destroy the integrity of the antibody. So in either case, the drug testing will be interfered, and there will be no result. Do we measure oxidizing chemical? Again, we mix with a very reactive reagent, which will react with the oxidizing agent. For example, we have a hydrogen peroxide already present in the urine. So if we use a reagent called tetramethyl benzidine, that will quickly react with any oxidizing agent present in the urine, and that will form a different complex. And by passing the light through that urine solution, and which will absorb a wavelength of certain frequency, and then we can determine how much the concentration of oxidant in the urine specimen. So in summary, laboratory result interpretation, we call it adulterated urine, adulterated with reactive chemicals. If somebody added very acidic or super base solution and interfered the pH. pH is no longer within the 4.6 to 9. Somebody added nitrite, which concentration is greater than 500 milligram per deciliter, or chromium concentration of more than 50 milligram per deciliter, or in general, any oxidant at the concentration of 200 milligram per deciliter, and there is no consistent between creatinine and gravity. Any validity parameter fails, then we call it adulterated urine. We classify the urine specimen as substituted if specific gravity is super low or super high, or creatinine is less than 2 milligram per deciliter. We report urine specimen is diluted if creatinine concentration is around 2 to 20 milligram range. And we report urine specimen is invalid by any validity parameter, invalid by pH, or invalid by specific gravity, creatinine concentration, or invalid by presence of oxidant, or if it looks very bad, viscous, and the laboratory technician will follow the lab SOP and determines that the texture of urine is no good for running it on the instrument. So in summary, what we learn here is when we are using a principle photometry to measure the urine validity parameter in all validity assays, which means that we're using light, we're using certain wavelength of light. For example, if we have a light source and we convert that light and then into the component, because the light has a different color pattern, like rainbow. And we have a device that has a specific wavelength that passes through a urine specimen, and then that particular wavelength will hit the photocell and then give a signal. So this is the photometry is general principle for all the validity testing, and there are various types of photometry analyzers, which uses many types modification of this principle as colorimeter, spectrophotometer, or fluorimeter. Welcome to my second part. I'm going to describe present about the drug screening by immunassays. And now I'm taking you to the lab. This is what the immunassay analyzer looks like. a big instrument, you can put reagent in one side of the instrument, and it has a lot of robotic handles. It can walk through the sample reagent and then sample the urine specimen, mix together, and then pass to the spectrophotometer to give the final result. This is more automated analyzers. You put the sample and you get the result in the computer. And all the validity assays and immunoassays are measured in this type of instruments. So the principle of immunoassays for the drug testing, the first reagent we need is a drug-specific antibody. And that drug-specific antibody will react with a drug and then form an immunocomplex or a drug-antibody complex. And then what we do is we quantify that DY complex, that antibody-drug complex. So how do we detect DY complex? So when antibody and drug makes a complex, then we need some kind of probe, how much that product is formed in that specimen. And we use a certain certain kind of probe to determine that. Just like you can measure the temperature of a barbecue meat with a thermometer. The probe here are certain type of enzymes. And these enzymes are labeled with drug itself. And when we put a substrate for that enzyme in that specimen reaction, then this enzyme will form a color product. And as we know from a photometric principle, there will be a color form in the reaction, and then we put into the spectrophotometer, and then we read how much DY complex is formed. So to summarize here, these are the reagent for a particular immunoassay, drug immunoassay. First reagent is antibody, which is specific for that drug. A antibody for morphine will not react with an antibody for TLC. And the second reagent, we need a probe, which is most of the time an enzyme, which is labeled with the drug itself. And as we saw in the previous slide, we need a substrate for that enzyme. And then we mix all together in a test tube and then put on the analyzer and read the final measurement. There are various types of drug immunoassay available in the market. The most common one is enzyme multiplied immunoassay. So in this assay, our antibody is a drug-specific antibody, which is a reagent 1. The probe, which is reagent 2, is a glucose 6-phosphate dehydrogenase. And then a substrate reagent is nicotinamide adenine dinucleotide, and that will give a product NADH. So if drug is present, if drug is absent, the antibody will react with the drug with the probe, because the probe is also labeled with the drug. So here, you can see a hexagonal D and which has a red background, and you can see a drug with a black hexagonal background. They are the same drug, but I present it in 2 different colors to distinguish that the red background is associated with the probe, and the dark background is associated with the natural drug present in the urine. So when drug is absent, all the antibody is going to capture that probe, and then that will render the enzyme activity nil. There will be no enzyme activity, and you will see no signal. If the drug is present, then the probe and the drug present in the urine will compete for the antibody. And if drug is present at a very high concentration, all the drug present in the urine will be captured by the antibody, and our probe is free. Our probe can work on the substrate and produce a colored product. And this way, if there is no drug, we'll not see any color change in the instrument reading. And if there is a lot of drug present in the urine, then we'll see a lot of color change. It will give a directly proportional type of a linear increment of the concentration. Another type of common drug immunassay is called enzyme cloned donor immunassay, or CEDIA. It is also similar to the AMIT assay, but there is a little modification. Again, the first reagent is antibody, is specific to that drug. The probe is a different enzyme called beta-galactosidase. And substrate is chlorophenol red beta-galactosidase, or CPRZ. The difference in this type of assay is the enzyme itself is presented in two parts. The probe, you can see letter F, and in the substrate you have a letter L. So when you mix together, the enzyme will the parts of the enzyme will combine together and form a active enzyme. And then that active enzyme only can form the color product. So again, same principle. If drug is absent, antibody will capture all the probe, and there will be no signal. But if the drug is present, the antibody, the probe and the drug present in the urine will compete for the antibody, and a lot of the antibody will capture the drug present in the urine specimen. That will make the probe free. At the same time, the probe and substrate, the enzyme combine to form an active enzyme that will form a colored product in the specimen. And you see, as the concentration of the drug changes, the change in the color over the instrument reading will increase. Another not very common but widely used enzyme immunoassay uses a probe called microparticle. It's called kinetic interaction of microparticle in solution. So some kind of microparticle are used as a probe in this assay. These microparticles are labeled with drugs, and when drug is absent, the antibody will react with that probe and form a clump. And when we pass the light through that clump, there will be no absorption. And when there are drugs present in the urine, again, there will be competition between the probe and drug for the antibody. And the antibody will engage on capturing the drug present in the urine, and the probe will not form the clump, and there will be less light absorption. Another very less commonly used assay is fluorescent polarization immunoassay. In this case, the assay uses a probe which has a kind of dye. And the drug is the probe drug is labeled. The dye is labeled with the drug of interest. And same principle, if drug is absent, the antibody will capture the probe, and that will give a distinct light absorption. And when drug is present, there will be a competition between the probe and the drug present in the urine, and that will render that probe releasing the signal. There will be less light absorption. In other words, the principle is that when when antibody combines the probe, at that time, the polarized light can only produce the signal. Another less common drug immunassay is enzyme-linked immunassay, enzyme-linked immunosorbent assay, or ELISA. The different thing in this case is the probe is the enzyme has a probe, a secondary antibody labeled with the enzyme. And in this case, you have the first reagent, again, the antibody, and you have the probe, and then you have the substrate. When you mix all these things, then you need to wash your tube before you read the measurement. If the drug is absent, your everything is washed away. You do not see the signal. But if drug is present, then the primary antibody, which is reagent 1, will capture the drug, and upon that drug, the secondary antibody or the probe will react on it, and that will render the enzyme activity, and that will give the color change in the tube. That way, we can read the color and determine the concentration of the drug. So here are the very common cross-reactant for enzyme immunassay. Most interferences we see is amphetamine assay, because there are structurally similar compounds for the amphetamine in amphetamine immunassay. Methamphetamine, MDA, MDMA, chloroquine, ephedrine, pseudoephedrine, phenylpropylamine, tyramine, phentermine, ranitidine. All these chemicals can give a positive reaction with the amphetamine assay. Similarly, benzodiazepine assay, all the this assay, this immunassay, because all the benzodiazepine share a same structural chemical structure, benzidine structure, and all the assays will be reactive to the benzodiazepine. All the benzodiazepine available in the market will react with benzodiazepine assay. On the top of that, this chlorpromazine is another drug commonly interfere with benzodiazepine. Similarly, THC assay, naproxen, ibuprofen, salicylic acid, they all give a false result. For morphine or opioid assay, all these opioids, codeine, dihydrocodeine, heparin, hydrocodone, hydromorphone, oxycodone, oxymorphone, meperidine, they all can give a false positive reaction. And most important is PCP, because diphenhydramine and dextromethorphan, both over-the-counter drugs, they can give a false positive for PCP. I'm going to briefly talk about the point-of-care drug testing or dipstick drug testing. Dr. Ewan covered a lot of about this kind of testing yesterday. These are called the field testing. But again, the principle of all the immunassay applies to this test as well, which we call the lateral flow immunassay. This is the schematic of lateral flow immunassay or dipstick. And your pad has 4 regions. You have a sample pad where you apply your urine sample. And your reagent pad is coated with a probe, and which consists of a protein called hapten, which has a dye attached to it, as well as a drug of interest. On the capsule pad, you have 2 lines, and one line is coated with antibody that is specific for the drug, and another line which is coated with another antibody which is specific for the probe or the hapten molecule in the probe. So when the drug is present, for example, cocaine is present, what will happen is the probe will compete with the drug, and then in the test line you will not see any signal. But when the specimen flows from here to all the way to the control panel, the hapten will react and the dye color will be seen. When cocaine is absent, there will be no drug competing with this hapten molecule. So all the antibody reagent present in the test pad will react with the drug side of the probe and then give a signal. And when it further passes to the control line, it will react with the hapten molecule and produce the signal. So in summary, when drug is absent, you'll see two lines. But when drug is absent, you'll be see just the one control line. So some highlight of the DB stick testing. This is a web testing, so anybody can perform test. You do not need a specific lab space or a specific license to perform this kind of test. And within a single cup, there are all the tests, up to like 12 drugs you can test in one cup with oral duration test and validity test all built in one cup. And they are rapid. You can visually read the result in just 5 minutes, but it is not reliable. You can see a lot of false results, both false positive and false negative result with it, because the sensitivity is not that enough, and even at the low drug concentration, you get some kind of interfering signal, and to get a really good signal, the drug needs to be at very high concentration. And if there are more than 2 or 3 drugs, and there are always chances of cross reaction. So I'm going to summarize my immunassay part. You've seen that basically these are the photometric tests, and any substances, any chemical present in the urine that can absorb the light intensity at 340 nanometer or 570 nanometer can interfere with the immunassay test. And aspirin metabolite, which aspirin is a very common drug, over-the-counter drug. And if people are taking aspirin, their metabolite can interfere the assay that uses 340 nanometer wavelength. So all the amide assay can be interfered with this aspirin metabolite. And the most important is it gives a positive result for a group of drugs. It detects a certain chemical structure, and based on that, it will give a positive result for all the similar structure. To describe a little bit about how it is not specific, I have example of amphetamine. So amphetamine immunoassay, you have an antibody protein. It perfectly fits in that pocket, and it has a positive charge, and that reacts with some negative charge in the antibody molecule, and it gives a positive signal. But methamphetamine also fits in the same pocket. It has the same charge. It similarly binds with the antibody, and it will detect the methamphetamine as well. Not only methamphetamine, pseudoephedrine reacts the same way. And ephedrine also reacts the same way. So all these structurally similar chemicals will be positive for amphetamine assay. Is there any questions so far on the immunoassay part?
I don't see any in the chat yet, but I had a question about the cross reactivity, like with aspirin or ibuprofen. Do you have to have a lot of the over-counter medication in your system for it to react, or just taking a normal amount that could cause a false positive?
That's a very good question. Manufacturers who sell these assays have characterized their assay, and they have determined up to this concentration is reactive to this assay. In most of the cases, they needs to be really at high concentration. Normal 1 doses or past week use of aspirin will not be high enough to interfere with the assay.
Thanks. And if you could just try to go as slow as you can, because when you go fast, it gets hard to understand.
Yeah, okay.
Thanks.
So laboratory drug confirmation by mass spectrometry is very specific, very confirmatory test. The system configuration we have is a liquid or gas chromatography that is attached to the mass spectrometer. This is a very complicated instrument. And there are 3 parts in the mass spectrometer. The first part is ionization part. And there are a variety of ways we can ionize the drug. And the second part involves the mass analyzer. There are a variety of mass analyzer, such as triple quadrupoles, ion traps, and hybrids. And the ionized drug is detected by the detector at the end of the analysis, and which we can read in the form of chromatograms. This is a example of mass spectrometry. You can see a liquid chromatography here. This instrument, which has these liquid solvents, and you have a column inside, and then it is a liquid flow system. The drug passes from liquid chromatography to the mass spectrometry. And then mass spectrometry, this is the front end is the ionization part, and it has a vacuum tube inside, and which is a mass analyzer, and then it finally goes into the detector, and then we can read the signal in the computer. And these are accessories. Nitrogen generator is required to do the reaction inside this instrument. And they uses a very high vacuum. This is a vacuum pump. They suck all the air and all the detection. The mass spectrometry is operated under vacuum. This is a picture of gas chromatography. Its name implies your gas chromatography needs a gas to run. So we use a nitrogen tank to flow into this chromatogram, GC chromatogram, and which goes into the ionization and mass spectrometry part on the other side. So a general comparison between GC versus LCMS. GCMS is a old technology. It is basically used for volatile and water insoluble molecules, for example, hydrocarbons, perfumes, waxes, and oils. LCMS is used for water soluble compounds, for example, drugs and drug metabolites. For GCMS, we need to convert our analyte or the drug to something that is that can be evaporated, that can form a gas. So to do that, we need to do a chemical reaction by derivatizing a chemical, and we do not need that kind of reaction for LCMS analysis. So LCMS analysis is more straightforward, and the speed of analysis is also fast with LC, and the sensitivity is very, very high with LCMS as compared to GCMS. So most of my presentation will focus on LCMS because LCMS is taking over all the drug confirmation in the laboratory, and which is more reliable than GCMS. Let's talk about the chromatography part, chromatography principle. This is a very simple principle. You can see if you have a small blotting paper, a filter paper, or a paper that can absorb water, and then cut into a piece and then make a marker line at the top and dip it into the water, it will absorb the water. And your black dark marker will slowly separate into different color inside it. You can see here that black line when it is dipped in the water, slowly separating into a yellow. I can see blue and some purple color. So the chromatography is separation of colors, and this principle is utilized by the companies to make the chromatography material. So the key concept here is for the chromatography to perform, you need a stationary phase, which is a paper, a filter paper here. You need a mobile phase, which is a water here. Your analyte or a drug, which is a black line marker here. And then as you make your mobile phase move through your stationary phase, this color will be retained at a different time, which is called the retention time of each color, or when we get to the drug, retention time of the drug. In real example, this chromatography has a more complex column. You can see a small LC column in the side, which is 5 centimeters long, and it has a chromatography material, silica particle, a densely packed silica material inside it. And you have a GC column, which is 30 meters long, and it has a silica particle packed in it. So the same principle, your silica particle is stationary phase, which is inside that column. And then when you move your mobile phase through that stationary phase, basically water in the liquid chromatography or nitrogen gas in the gas chromatography, your drug will have a different affinity with the stationary phase, and they will elute at different time. For example, you can see amphetamine and THC eluting at different time. Your amphetamine does not have any interaction with the stationary phase, and it will elute within a minute from the column. But your THC molecule is a large lipophilic molecule, which will remain in the stationary phase for a longer time and elute at the later time. And this way we can separate amphetamine and THC and get a signal at two different retention time. This is how a typical chromatogram looks like. This is a LC column, liquid chromatography column, in which a mixture of 9-barbiturates and salicylic acid was separated in 3 minutes. So each peak represents each drug at different time. And we can quantify each peak based on their signal intensity and their area under the peak. The second part in this mass spectrometry analysis is ionization part. We heard a lot about the drug ionization yesterday in Dr. Eon's presentation, and a little bit similar principle here. So you have a neutral drug, and your neutral drug cannot produce a signal in the mass analyzer. You need to convert it into some kind of ion in a different way. There are several ways of producing the ion out of the drug. You can see a neutral drug here. It has a protons and neutrons with a positive charge, and your electron cloud outside that nucleus and you have equal number of electrons and negative charge and positive charge, and the charge is zero. There is no charge. There are equal number of negative and positive charge. One way GCMS we do ionization is a hard ionization. We remove one of the electrons from the compound, and then we form a drug ion. You can see here in this figure a drug ion produced in the GCMS, where we knock off this electron, and it has the same mass, but now it has a charge of 1 because it has positive charge of 1 because you lost 1 electron here. In the LCMS, the ionization process is more soft. Instead of knocking that electron off, we gently attach a positive charge into the molecule. Here, a drug ion formed in the liquid chromatography mass spectrometry mass analyzer is mass of 1 plus 1, m plus 1, because you added 1 positive charge, and you had a charge of 1, so that the mass to charge ratio is m plus 1. So more into the drug ionization fragmentation, a real example in the GCMS, example of methanol. You can see a methanol, which is a small molecule, which has carbon and hydrogen around it, and oxygen and hydrogen. And this dot represent the electron. So we have these many electrons, and it has a mass of 32. And when you hit this molecule with a high voltage electron, which is 70 electron volt, you're breaking this electron. You're removing one of these electrons from here and then creating a positive charge. Because you just removed 1 electron, the overall mass of this now a positively charged cation is 32. Because you knocked off the electron, this becomes a radical, very unstable cation, and it further breaks into the other 2 parts with just losing 1 hydrogen gives a mass of 31, or if it lost 2 molecules, both oxygen and hydrogen, it becomes this part, which has a mass of 15. So basically, in the GCMS chromatogram, you will see this kind of the chromatogram with fragmented ions. This is how drugs are ionized in the LCMS, in the source, in the first part. So when the separated drugs from the chromatographic column enters into the ionization area on the front end of the mass spectrometer, it forms a small droplet, and that loses all the solvent around it. And you applied a very high temperature to dissolve all those solvent, and you form a positively charged molecule. So we covered the chromatography principle, we covered the ionization part. I'm going to briefly describe about the mass analyzer on this system. So this is a typical example of a quadrupole mass analyzer. You have 3 chambers within the mass analyzer, and there are 2 filters. The first filter in the first chamber, which is here, will select the parent ion. You can tell the instrument, hey, just there are like thousands, millions of ions formed on the ionization part, but just take a morphine, or just take a THC molecule, which has a molecular weight, which has a charge of this much, and then it will typically take that one selected parent ion into the second chamber, which is Q2, where we apply a certain amount of energy to fragment that molecule. And then there is another mass filter at the entrance of third quadrupole, where you can again program your instrument. Hey, just take this fragment for this molecule, and then the way you program your method, it can give you a signal like this. For example, in this method, I picked up a morphine which has a drug ion mass of 286, and then when 286 passed from here to here, it fragmented into 201 and 165, and then only these two fragments passed through Q3, and I got a signal like this. More detail about the fragmentation of morphine in the previous slide here. Not only two, if we apply a certain energy in that second chamber, we can fragment that morphine molecule into several small fragment ions. You can see from A to Z here, different ions. And this is a kind of fingerprinting of that morphine molecule for this kind of mass spectrometry analysis. So every time when you have a morphine in your urine specimen, the instrument will see all these ions, and as we program the instrument, we'll pick certain ions out of it to quantify that this is the footprint of morphine. So I'm moving more into the data analysis part now, which is, once you have the mass analyzer, all these mass drug ions passes into the detector, and we get the signal chromatograms in the computer, and then we do the data analysis. Before that, I want to talk a little bit about the isotope level internal standard. This is a very important concept in the drug conformation. You can see two structures here, a morphine structure and a morphine D6, which is a isotope level. What does that mean is 6 hydrogen from the morphine molecule has been replaced with a different type of hydrogens. In nature, we find 3 different types of hydrogen. The protium is the common hydrogen, which is 99% availability in nature. But we have a deuterium, which has a 2 proton, and which has a neutron, and we have a tritium, which has a 2 neutron. So we call it one hydrogen of mass 1, hydrogen of mass 2, and hydrogen of mass 3. So when we replace all the protium from morphine molecule with a deuterium, another isotope of hydrogen, the mass became 291. So you have a second hydrogen here. If you replace 6, then 85 plus 6 is 291. And the morphine forms the parent ion at 286, and the morphine D6 forms 292. And these two ion is entirely different for the mass spectrometry mass analyzer. Mass analyzer will behave these two things entirely different, two species, two different signals. But from the chromatography, because we just change the hydrogen, will not change the retention property of these two molecules. They will coelute. So these morphine and morphine D6 will coelute at the same time, but when we see the data, we can see the mass spectrometry differently detecting morphine and morphine D6. In other words, if you look at the chromatogram, if drug is absent, we can see morphine D6 at the retention time 2.74. When drug is present, we can see a drug as well as the internal standard signal, which is a pink line here, at the same retention time. So they coelute and they guide us where the morphine is to where the morphine chromatogram is to find. And before moving to data, this is another concept in the mass spectrometry confirmation. So for any chromatographic analysis, we need to do some kind of purification of the sample. For example, we can have a urine specimen and we add more water to it to dilute the interferences, or we can use a different types of extraction technique to purify the sample. So with all this process, we finally get this kind of data in mass spectrometry. This is a calibration curve, and you have a 3 calibrators here. What you're seeing here is a quant ion, which is the first transition for a drug, and its internal standard. And for each concentration level, you have a signal, and your internal standard concentration signal will normalize that the signal, and you get a linear curve like this. And basically, a calibration has a cutoff at a certain level and a upper limit of quantitation. And your lower limit of detection that you can see at the lower end of the calibration curve is lab specific, instrument specific. If your regulatory agency requires this level of cutoff, then lab has to develop that. This is our LOD. They have to optimize their assay, which is not uniform across the lab. So how do we make the structural confirmation in the mass spectrometry analysis? We have at least 2 transitions analyzed in the mass spectrometry. Again, we have the parent molecule. We can fragment into so many fragments. So we basically take 2 fragments. The first fragment we quantify, and second fragment we compare the 2 fragments. Here, a morphine molecule 286 is this peak for morphine 286 fragments of 201. And this signal for 165 fragment. And when I overlay this signal over this signal, I should get a certain ratio of the fragments. That tells me that these 2 fragments actually came from the morphine molecule, so that I can confirm in the unknown sample. Another important part in the data analysis of chromatographic data is a quality control. Usually you have a known amount of samples. You add known amount of drug into the urine specimen, and you analyze them along with the drug, along with the unknown specimens. And basically there are 2 controls at low end and high end. And if these controls behave very well, if the accuracy of these controls is good, we consider the assay is good. So how do we confirm the specificity in the mass spec? So mass spectrometry analysis gives us a better specificity, unlike a dipstick testing or immunassay testing. We have a certain degree of specificity in this kind of analysis. And the first of all, we've seen that we have a chromatographic separation. Each drug has its specific retention time. And we confirm that retention time by adding its analog isotope level internal standard. And we identify the molecular ion, by its mass to charge ratio. It's specific to that drug. So it's more specific. And the most important is we fragment that parent molecule into the fragment ions, which gives a kind of fingerprinting, which is called molecular fingerprinting. For example, I've given the example of morphine. So this is a typical morphine fingerprint. You have a morphine molecular ion of 286, and it should fragment into 201 and 165, always in the certain ratio. And we compare these molecular fingerprinting with authentic standards. And on all of this specificity, we also analyze parent drug and its metabolite altogether. So we have a metabolic pattern as well, which is not possible with other lipstick testing or immunassay testing. So there are limitations with mass spectrometry analysis as well. It's very technical and very complex. You need a very good laboratory training to run these instruments. And I briefly talk about sample purification, which is very complicated with GCMS analysis, needs more resources, very laborious process. And with LCMS, we see a lot of matrix effect. No matter how you purify the sample, there is always some kind of ion suppression or ion enhancement in the ionization part of the instrument. That sometimes gives some inaccuracy in the result. Not only with that, the matrix effect, we see chromatographic interferences as well. There are a lot of chemicals that may collude with in the chromatographic separation. And most importantly, for the mass spectrometry analysis, this is a laboratory developed test, and the test needs to be well developed, well validated, and very robust. And it is specific to the lab. Lab has their own method. The quality of their method depends on how robust, how well characterized that method is. Now I'm going to move on to my final part of my presentation, quality assurance. Measurement error. So with every measurement, there is some kind of error. If you look at a volumetric flask here, you're trying to measure 20 milliliter here, and if you look at from right angle, you will see 19.70 milliliter. But there are different views which can give a error rating, and with each measurement, there is a margin of error. There is an uncertainty involved in every measurement. In this beaker, you can see this beaker can measure 200 milliliter, but with margin of error of 5%. So anywhere between 190 to 210 milliliter can be measured if we use this beaker. And when you do a replicate measurement of using this beaker to measure something, then you can find out your margin of error, and you can estimate that margin of error with certain level of confidence. And when your error factor within 2 standard deviation, we generally consider 95% confidence interval. And this applies to the laboratory measurement as well. When you receive a lab result, then it should have a margin of error. It should have a specified confidence of measurement. So in laboratory analysis, there are various sources of error. The measurement error can come from the sample itself. For example, maybe the sample is clotting, there are interfering substances, people take variety of food, variety of things, and their urine is so different. It depends on what kind of diet they had. And it can come from the operator to operator variations. It can come from laboratory environment. Not all the analyzers, all the instruments behave same way when there is a fluctuation in laboratory ambient temperature, other things. Reagent, quality of the reagent is also important, and itself the other factor, measuring system, your mass spectrometer, how calibrated it is, how well maintained it is. All these factor adds up to the incorrect test result. So method validation is important part in drug testing, because during this process, during the method of validation, we characterize all these errors, and then we can say that our measurement system may have these many errors. Our error margin is this. Our confidence is this. So for the immunassay drug screening, they are generally FDA approved tests. The commercial manufacturer do all these assay characterization, and the lab who uses this assay from the who purchase this assay from the vendors need to exactly follow the manufacturer instruction. If they want to deviate from anything from the FDA approved test, then they have to do their own lab validation. For a mass spectrometry drug confirmation, this is not a FDA approved test. This is a lab developed test. And the lab scientist has to validate all the parameters, and they have to characterize the assay. And when we validate the assay, we basically look at accuracy of the assay, precision of the assay, limit of detection, what will be the cutoff, what will be the upper limit of detection, and what chemicals or other drugs can interfere with this assay. All the possible sources of error we characterize during this process. And to estimate the uncertainty in the laboratory measurement, there are two approaches, which is widely used in forensic practices as well. Nordic approach, which was developed in the Nordic countries, which is very simple form, and ISO GOM approach, which is more comprehensive, which involves all the sources of error that we just mentioned, and modeling of all the sources of error, and then calculation of final uncertainty. So in brief, at least the uncertainty measurement should include uncertainty factor from the standard, which means all the standard used in the preparation of laboratory standards, uncertainty from the calibration bias, calibration curve bias, uncertainty from the assay precision, uncertainty from the assay bias, which is a systemic error in the assay. So Nordic test approach is simple in that it everyone can in the lab with a basic knowledge can compute the uncertainty, because each laboratory assay is run with a set of controls, and from those controls or repetitive measurement of controls, we can estimate the assay precision and bias, and from which we can determine the uncertainty of that assay. So ideally, when you have a drug report, you should have the analyte and the concentration with margin of error. For example, if you see the laboratory result for morphine, if the instrument gave a 200 nanogram per milliliter, but should come with the margin of error of that lab for that particular analysis. and they should specify what is the confidence level for that analysis. And that will give a good, if you see a margin of error and the confidence level of that error, then you can consider that lab result is has been well characterized method and is a good result. With this, I conclude my presentation. If you have any questions, I'm happy to take it.
Thank you so much, Dr. Driscoll. That was awesome. A lot of great information there, and I think you broke it down really well for us. One question was about why would a lab choose to do like GCMS versus LCMS or the reverse? Like, what are the pros and cons of each?
So LCMS, the history of LCMS is recent. Labs started to use LCMS in their production facility not long time ago. But GCMS historically 70s, 80s, the ideal instrument was GCMS. So many labs are just used to GCMS. If you consider federal drug testing, NLCP, National Laboratory Certification Program, which oversees the federal drug testing program, their regulations is still they heavily dependent upon the GCMS analysis, and they are slowly evolving. They are making their changes now. Not all the drugs, opioids and amphetamines can be done on LCMS, but not like few years ago. Their recommendation was GCMS. But the sensitivity of LCMS is very high and is more robust analysis than GCMS.
Okay. And if you could go back a slide when you were talking about the uncertainty of measurement.
Here?
Maybe back one more. Sorry, can you go forward again? Well, I'll just ask that question. Maybe you can find the slide, or maybe we don't even need it. So the question was about the 95% certainty. If the analyst is 95% certain, does that leave 5% possibility of error?
Error in terms of if your quantitation is, for example, 100 nanogram, labs is 100 nanogram, but it can be within certain if it is within 95%, and then their error margin is 20%. So you are 95% confident that your analysis, no matter where you take it, will be anywhere between 80 to 120 with 20% error. But the error, the 5% error would include that in 1 in 20 analysis, if you repeat that analysis 20 times, and one time it may be not 80, it may be 75, or it may be 125. Does that make sense?
I think so, with respect to weight, but what if you're identifying like the substance as morphine and you're 95% certain? How would that work? Like 5% of the time it might be something like morphine, or?
No. It will be morphine. 5% of time it will be morphine, but your quantitation 100 nanogram will not be 100 nanogram. It will be 75 nanogram or 130 nanogram. Okay. It is no longer within 20% margin error.
So the uncertainty budget is for the amount, not for the identification of the substance?
Yes, correct.
Okay. If there's any other questions, feel free to write them in the chat. And if not, we will move back to Dr. Evans. Thank you so much, Dr. DeCall. And you'll stick around for the Q&A at the end, right? Sorry, I think my internet might have cut out for a second. You'll stick around for the Q&A at the end, right, Dr. DeCall?
Oh, yes, correct.
Okay, great. Well, we will switch over to Dr. Evans then. Thank you so much, Dr. DeCall, and we will chat with
Thank
you
you, Sarah.
at the end. If people have more questions, just add it to the chat.
Okay. So do you see a slide that says example lab reports?
Yep, looks good.
Okay. All right, so we're going to end the class with looking at example lab reports, and if we have time, go through scenarios where we can try to interpret the results from these reports. So I've taken actual lab reports from some of the cases I've worked on from several different laboratories, and this is to show that each lab has their own method of reporting these results. So you're not always going to find the same information from one lab to the other. And so we're going to try to find out what information we can find from these different labs. So here, this lab is ExpertTox. They did, they give this overall report. The main part that's going to show the information that we're interested in is shown here in red.
If people need to zoom in, they can, well, there you go. Or they can use the zoom in on the left side of your screen. You should see that if you want to zoom in.
Okay. Yeah, most of these I've just cropped out a certain part of it, but some are bigger than others. So this one is from ExpertTox. It shows you the test name. This is a 5-drug panel screen. This was run LOD at the limit of detection. So that pretty much means that if they find anything, they are going to report it. Anything of these 5 drugs that we're looking at, which include marijuana, amphetamine, MDMA, or MDA, methamphetamine, opiates, cocaine, and phencyclidine. Actually, that doesn't add up, right? So no, they have one test for amphetamine and methamphetamine, opiate, cocaine, phencyclidine, and marijuana. In the media, it says this is a hair test. And under lab results, everything is not detected except for amphetamine. They are showing a confirmed value of over 2,000 picograms per milligram. So this has gone through the immunoassay screening with a screening cutoff of 300 picograms per milligram, and then went through a second test. So the screening test, if you look down here in the footnotes, screen analysis was through ELISA. Dr. DeCall talked about that. That's the one where you have to wash the sample in between 2 steps. And then they used a confirmed test they show over here, which is LC-MS-MS, so the liquid chromatography mass spectroscopy. So this is the information that'll get you. So they are showing amphetamine, but not methamphetamine, which is interesting. Amphetamine is abused, but not as much as methamphetamine. if they were to report methamphetamine without amphetamine, which is a metabolite of methamphetamine, then you would have to question the results and whether or not that was a valid test. Since without the metabolite, something did not work right. So this one is from the North Carolina State Crime Lab. Their reports are very different. So they don't have a nice little table. Instead, they basically have a little mini affidavit to just tell you textually what the results are. Zoom in here. It's an affidavit talking about the analyst, that the analyst has their permit, has an active permit to run the tests. And then in this third paragraph, they start to say, okay, what they tested was blood. And then down here, these are the results. So this was a blood alcohol test. They are reporting 0.03 grams of alcohol per 100 milliliters. And here they're actually giving you their error rate. So the actual measurement was 0.036 plus or minus 0.002. So this is kind of nice where they're giving you the error rate. And you can use that if this was a measurement that was right near a certain cutoff. You can use that and see, was the cutoff between a positive or negative within the error rate of that machine. Most labs do not necessarily give you an error rate. So this is from the FBI lab. Here we've got a table, and also lots of footnotes to go with that. So if we look closer, the FBI here is reporting that this was a blood test, that they tested in ethanol. They got less than 0.01 grams percent. And then they've got these little footnotes, so you then have to come down and kind of help interpret what they're telling you with their footnotes. So here, cocaine, opiates, amphetamines were not detected. That's easy to see. Benzodiazepines, they identified diazepam, nordiazepam, alprazolam, and tamazepam. All right, some of these get a little weird. So then you have to go down to notes 2 and 4. So note 2 is saying they used liquid extraction and ultra performance liquid chromatography with high resolution mass spectroscopy. That's just one of the instruments for that. And then for number 4, they are saying that this analysis was with 2 different drug screens. So the problem is here with the diazepams, they're saying that these are detected, but they're not telling you how much is actually in there. And that's problematic because in order to get certain interpretations about intoxication, you need to know how much is there. So we look now at the THC for marijuana use, and here they are reporting concentrations. So that's a good result that can help, that you can interpret. And under their footnotes, number 5, they are saying that this was a confirmation test, not just a screening test. So that's why you're getting actual quantitative numbers. The Defense Health Agency, so this is a military drug test. it doesn't have much of a table. I love it when the labs just have a nice table. You can just look at it and tell what the results are. But some, they like to do these textual results. So you have to go through it. No ethanol was detected. It was positive for diazepam. Oh, sorry, let me blow that up. So they tested blood. There was no alcohol. They tested blood for drugs. They tested it for amphetamines, barbiturates, benzodiazepines, marijuana, cocaine, opiates, PCP, and other amine drugs. They found diazepam, and it was a confirmed test, so it wasn't just the immunoassay, which is a screening test. It was also confirmed by liquid chromatography and tandem mass spec, and they report a result of 883 nanograms per mole. So some of these you really have to look into and read. NMS Labs is very well-known contract lab. They do lots of work in North Carolina. I like that they, again, have these nice little tables that you can look and figure out what happened. So here we've got positive findings. They found alprazolam. They found 11-hydroxy-THC, carboxy-THC, and THC itself at these different concentrations. These units, this was all in blood. And to get more information, they tell you the type of test that was run, which has a code number, 8150B. The B at the end means that it was tested in blood. This could be 8150U, and that would mean that it was tested in urine. And then this is called a DYD-DRE drug panel. So this would be something usually you looked at for drunk driving or drug driving. And what you can do, so here they're telling you the positive findings. If you want to know what else they looked for and found that was negative, you can go to their website and they have a test catalog. You put in the code number for that test right down here in your test catalog, the 8150B, and that will bring up information about that test. They're saying it's an ELISA, so that is a screening test, and they're going to be looking at amphetamines, barbiturates, benzodiazepines, buprenorphine, marijuana, carisoprotanol. Sorry, I always have trouble pronouncing this one. Isopropyl prodiol, cocaine, fentanyl, methadone, and methamphetamine. So since they're only reporting positive results, you need to come in here to find out what was negative. And yes, it's saying an ELISA test, which is a screening test. But when they are reporting numbers, then that means it was positive in the ELISA test, and then they went ahead and ran a confirmation test. So let's see, I don't think this says, okay, sorry, if you go back to the full report, so they have their positive findings over here. So this is like a quick and dirty look. And then more detailed findings, which is pretty much the same information as on the other table, but it does give you the assay that was used in the confirmation, which is LC-MS. So you can find all the information, but sometimes you need to go to their website and look up that assay to get some more details on it. what they actually did. This lab report is from test country. Details are shown here. So they looked at hair, and they looked at a 5-panel of drugs, which includes amphetamine, cocaine, THC or marijuana, opiates, and PCP. And I know that labs like to limit the amount of space that things take up. So they like these little 3-letter abbreviations and use that a lot. But sometimes that can be confusing. So what in the world is COC? What kind of drug is that? You gotta, might have to try to look that up, Google it maybe, to see if it's commonly used. So that usually would be used for cocaine. And here they're saying the verified results are that this was negative for these drugs. So realize too that it's negative for these drugs only. It could have been positive for something that wasn't part of this 5-panel test. Redwood Toxicology Labs. These are, I believe they're in California. So we don't see that a lot in North Carolina, but I have seen some cases that use Redwood. So they have a nice table. Here the specimen is urine. The tests that they were ordered here, they're like NMS labs, they're showing you the test code. So you could go back to the Redwood Toxicology Lab website and look up that test to get some more details onto what they did. So they looked for amphetamine, and they did a screen of 10 different drugs, and also looked at alcohol and oxycodone. Here the results are, they're saying amphetamine was detected using GCMS at 1915 nanograms per milliliter. And down here, they kind of break it down into results for the screens and for the confirmation. So here you look at the screen. They are so the results are all non-detected for everything except for the amphetamine. So that means that none of those drugs were in that sample at these cutoffs in the screening test. Amphetamine was at least 1,000 nanograms per milliliter during the screening test. And then from that screen, they ran it through a confirmation test, gas chromatography mass spec, and detected the almost 2,000 nanograms per milliliter. And since this was a urine test, it's important if they will also report the concentration of creatinine. Sometimes you can compare the drug concentration to the level of creatinine, which some people can argue that would be a more accurate result than just the concentration based on the volume of urine, because of the sort of constant level of creatinine in the urine. It does vary a little bit depending on how hydrated a person is. So if you've got a dilute urine, sometimes if you calculate the concentration based on creatinine instead of the volume of urine, you might argue that that's a more accurate measurement. But I think that's a little controversial, and most labs will report just based on volume of urine and not based on creatinine. This is LabCorp. Here they're giving us a nice table to look at. So we've got hair, that they're looking at opiates. The results are negative for cocaine, PCP. I guess they're saying hair standard plus opiates. So a standard might be a drug test, which includes cocaine, opiates, PCP, amphetamine, and marijuana. That's usually the common ones that are looked at based on the Department of Transportation's regulated drug testing. So here we've got a positive for opiates, and then they break this down further. They've got, apparently they have a separate screen for morphine and 6-monoacetylmorphine, which is a marker for heroin. And that's kind of unusual to see a specific screen for monoacetylmorphine. They must have very specific antibodies for that. And then they report the confirmation. So usually, if you're trying to differentiate whether or not the result was a screening test, which cannot be, shouldn't be taken into court as evidence, and differentiate that from your confirmation test is whether or not they're giving you an actual number value for that concentration, or they're just saying positive versus negative. This one is kind of interesting. LabCorp doesn't actually do their own testing for hair sampling. So we've got hair, LabCorp is reporting it, but if you look over here under lab, they note that all of these tests were done at lab 1, and the chain of custody protocol was done at lab 2. So lab 2 is actually LabCorp. So they took the sample, they now have custody of it, and then they sent it to lab 1, which is psychomedics. And psychomedics actually did the testing, but they're reporting it as if it was LabCorp. So, and I think that's only for hair that LabCorp will contract out for psychomedics. So if I get a case where I've got urine and hair tests or blood and hair tests, I like to make a timeline to kind of explain what all the information means. So here we've got scenario 1. All the positive tests are in red, all the negative tests are in blue. We have 3 urine tests that were taken January 5th, 2020, February 21st, and March 1st. Because it's a urine test, they have a window of detection of about 3 days or so. So the size of this block is to represent about 3 days or so. And there is a hair test taken on March 7th, and that window of time usually covers about 3 months. So here you've got 2 negative urine tests and 1 negative hair test and 1 positive urine test. Here they're reporting just methamphetamine. They're not reporting the amphetamine. So if you were to get results like this, then you could say, first off, because there's only methamphetamine and no amphetamine, that this positive test is really under question. And since you're bracketed by negative urine tests and that same time span that the positive urine test covers also has a negative hair test, that chances are that this positive urine test on February 21st is not a real positive test. So then scenario 2, you've got methamphetamine and amphetamine in this positive urine test. So now you can't argue that maybe it was from environmental exposure. The methamphetamine most likely was in their body, got metabolized to amphetamine. So that person had consumed that drug. But you still have negative hair results. So what this means is, yes, probably that person did take methamphetamine on February 21st, but because your hair test, which covers that time, is negative, this was probably a one-time incident. If they had taken methamphetamine several times, if they were an addict, they would have a hard time only taking methamphetamine once over a span of 3 months. So more likely than not that this was just a single-time incident. Now, here we have 3 negative urine tests and a positive hair test. Both methamphetamine and amphetamine are showing up. So again, the drug was found within the person's body. It wasn't just environmental exposure. So this usually would represent a case where the person knows that the urine test is coming and they will stop taking the drug for a few days and let it clear out of their body, and then they can take the urine test and then resume drug use again. As long as they know when that the urine test is going to happen, they can try to avoid getting detected. But because the hair test continuously monitors for drug use, there's not a chance for you to just stop using it and hope that it clears out through your hair if you're a drug addict. If you're able to avoid the hair test by not using the drug for 3 months, then I think you could argue that that person is no longer a drug addict, or at least they're not an active drug addict. Maybe they'll relapse later, but if they're clean for 3 months, how much of an addict can they really be? So we've got a few more minutes left, so I think we can do a couple cases here. So here we have a man on probation. He had a prescription for morphine used to treat pain for recent surgery. But his probation officer found him in violation of his probation for having found hydromorphone in his urine, and he was only prescribed morphine. So hydromorphone is a much stronger form of morphine, similar to the level of fentanyl, but probably not quite as potent. So the results are 300 nanograms per milliliter of morphine and 2 nanograms per milliliter of hydromorphone. So the question is, did this probationer violate the terms of their probation by using a non-prescribed opiate? So, didn't mean to see that so quickly. If anybody wants to try to put something in the chat, we can do that. I actually cannot see the chat right now for some reason.
I can let you know if we get an answer there.
Okay. Okay, so the answer is no. And the reason is that hydromorphone is a minor metabolite of morphine. So because you see the hydromorphone at a lower concentration, a much lower concentration than the morphine, 300 to 2, you can be pretty confident that that hydromorphone is coming from the use of the morphine and it just getting metabolized to a small amount of the hydromorphone. So yes, you'll find that drug in the urine, but that doesn't mean that they're using your probation. A teenager applied for a job. They had to take a hair test before they were hired. The drug test came out with 1 nanogram per gram of THC. The potential employer refused to hire them because they tested positive for THC. So the question is, was that a correct choice? Did the drug test show that the person consumed marijuana? And again, this is a no, because we only found THC. Normally, you would find that THC is a minor component in your testing, and that you're going to see more 11-hydroxy-THC or THC carboxylic acid, the two major metabolites. So if you're not seeing that, it's probably from an environmental exposure. So maybe this person was at a concert or something, an area where people were smoking marijuana, but it does not show that they were consuming marijuana themselves. A man was on probation. We were required to take a breathalyzer test 4 times a day. So this question is actually based on a case that I had. It was not in North Carolina. There are some states, people on probation will be required to use a breathalyzer multiple times a day to show that they're not consuming alcohol. Okay, so this probationer had to use a breathalyzer 4 times a day. After being on probation for 10 months, they had a positive reading on one morning, and they did not have a positive result after that. The probation officer said that they violated their probation and were going to send them back to jail. So then the probationer had a hair drug test done to look for alcohol. And in hair, you're not really looking for the alcohol itself, you're looking for the minor metabolite ethyl glucuron. And the hair test showed that it was negative. So, person's been testing negative for alcohol for 10 months. They have one single test that came out positive, and the probation officer is going to send them back to jail. So did they drink alcohol? So they didn't prove that it was alcohol, because if you're taking 4 breathalyzer samples a day, and only 1 out of those 4 is going to test positive, chances are they did not consume the alcohol, because it would have stayed in their body long enough for a second test to test positive. Plus, you have the problem of mouth alcohol, where if you have something in your mouth that contains alcohol, you can test positive, but it was never in your body, and you were not intoxicated by that. The fact that this person was conducting these tests for 10 months, 4 times a day, means they were taking hundreds and hundreds of breathalyzer tests. Every test has a certain error rate, and the chances of just by chance getting a positive reading over 10 months are pretty high in a situation like this. A female was on probation. tested for drug use with a screening urine test that came up positive for cocaine. A confirmation test was done and it was found to be negative for cocaine. On another incident, the urine screen was shown to be positive for methamphetamine, but not amphetamine. When the confirmation was done, it was found to be negative. The probation officer thought the defendant was using drugs, but somehow cheating on the urine test. So they ordered a hair test to look back at 3 months of possible drug use. The hair test was positive for THC in the screening test, and the confirmation was positive for THC, but not its metabolite, THC carboxylic acid. The defendant was charged with probation violation. So here, the probation officer is getting annoyed because they're seeing lots of tests come up positive on the screen, but in confirmation, they're actually negative. So they get the hair test and still want to throw them in jail, even though that the THC metabolite was not present, indicating an environmental exposure. So those are the cases that I have. And we are just at about 3 o'clock. So does anybody have any questions?
Yeah, thank you so much, Dr. Evans. We've had a few questions come in. One is, so would you recommend if there's a positive urine test, but the client insists that they've not relapsed or used, should you ask for a hair test?
Yeah, I think hair tests are probably one of the best defenses against positive urine tests. The one fallback is that hair tests are not as sensitive as a urine test, because instead of looking at what was used in a 3-day window, you're looking at a 3-month window. So if it was just a single use, it is possible for some single-use occasions to come out negative in the hair test. But if the argument also is, well, I guess it's 2 things. If your argument is you can't ever take any drug ever while you are, we'll say, on probation, and any kind of violation will send you to jail, then you could counter that the hair test is not going to be useful because it will miss a single use. But that can be argued against in court. But on the other hand, if it is a child custody case and you're really looking at, is that parent an active drug addict, then the hair test works great, because yeah, maybe there's a one-time slip up during the time of the hair and it still came out negative. But that means that person is not using very often throughout that 3 months. So I think that's a pretty strong case to say that they're not taking drugs. They're at least not habitually taking drugs.
Okay. We've had one other question, or 2 more questions. One is, and this may be for Dr. DeCall, how do prescription drugs like Ritalin or Vyvanse show up as amphetamines? So like in a lab test, how would you expect to see those ADHD drugs showing up?
I guess I can answer that unless Dr. Cole wants to. So Ritalin is not amphetamine. It is a completely different drug. So it may show up in a screening test as amphetamine, but once you get to the confirmation test, it will not show up as being an amphetamine.
Okay. have one more question that came in, but we're right at 3 o'clock. So I will, if you can hang around, Dr. Evans and Dr. DeCall, that'd be great. But I just want to thank both of you for your presentations yesterday and today. It was, you gave us a lot of great information. I thought it was a really helpful program. So I really appreciate all the work that you put into preparing for it. And I want to thank all the participants. I appreciate all the time that you've put into this training as well, all the great questions that you've sent. Program will send out, like I said, the link where you can report to me how many hours of CLE credit you attended. And also we'll be sending out the recordings and the materials, the PowerPoint presentations. So if everyone can, if you have the time, please hang out. We'll do a couple more questions. And if not, thank you so much for being a part of the program.
Yeah, thank you for lasting all this long. It's a long 2 days.
Yeah, it's a dedicated group. The other question that came in was about metabolites. So in hair testing, or I guess in any testing, if the metabolite is not present, does that mean that the exposure was environmental?
It's usually going to. It's going to depend on the metabolite and the tissue that you're looking at. So hair may contain certain ratios of metabolites that are different from urine or blood. So there might be a rare incidence where you're near a cutoff level for a metabolite that maybe doesn't show up very much in hair, but that would show up in urine. But I think for the most part, most metabolites that show up in urine are going to also show up in hair. It's just they may show up at lower concentrations than you would see in urine or blood. But for the most part, if you're not picking up any metabolites, then that's probably indicating an environmental exposure, or it's a drug that just doesn't get metabolites. So it depends on the drug.
Great, thanks. I'm not seeing any other questions in the chat. If anyone wants to unmute and ask a question, you're more than welcome to.
As I said yesterday, I'm going to try to create some mini classes that are maybe like 10 minutes long or so. If you want to send me an email or find me on alignable.com, I can make sure that I send you any of those classes that I create. It might be a month or two before I get to it, but eventually I hope to start making some more classes.
Great. And our plan is to put the recording